So this is a solution to quiz 2 from Unit 5. So we're taking an airplane from Boston to San Francisco, and we want to convert that distance into light seconds, special relativity units. So we've got 2,700 miles, and let's go from miles into kilometers. So the way that I remember that is that a 5-kilometer road race is about 3.1 miles. You could also remember that 1 mile is about 1.6 kilometers. But anyway, I like using that conversion. So 2,700 times 5 divided by 3.1, and I get 4,355. 4,355, and that's kilometers. And why do I do 5 over 3.1 instead of the other way around? It's because I want the units to cancel. Miles cancel with miles, leave me with kilometers. And now let's go into meters. They're 10.3. They're 10 to the 3 meters in 1 kilometer. So let's see, this is 4.355 times 10 to the 3 times 10 to the 3. That's going to be 4.355 times 10 to the 6 meters. And you can do that on a calculator if you prefer. So this tells me that from Boston to San Francisco, it's about, it's over 4 million meters. All right. So now let's convert to seconds using the speed of light. So 4.355 times 10 to the 6 meters. And there's 1 light second in 3 times 10 to the 8 meters, because that's the speed of light. Light travels this many meters in 1 second. So meters are going to cancel, and I'm going to end up in seconds. And let's do this. This one I definitely need a calculator for. 4.355 times 10 to the 6 divided by 3 times 10 to the 8 is, it's going to be right around 0.0145 seconds, or 14.5 milliseconds. So that's how long it takes light to travel from Boston to San Francisco. All right, so the next part of the question is asking for the speed of the plane as observed by someone on the ground. So what is this? This is a delta x. That's the distance in light seconds. Delta t is given in the problem. It's 6 hours, or 21,600 seconds, 21,600 seconds. So speed is delta x over delta t as usual, 0.0145 over 21600. These are both seconds. So let's do that. Divided by 21600. Oh boy, that's a tiny little number. 1, 2, 3, 4, 5, 6, 7. So that's 6.72 times 10 to the minus 7. So that's the fraction of the speed of light that the airplane goes. So this is v, the speed, expressed in SR units as a fraction of the speed of light. So now let's turn our attention to the third part of the problem, where we want to think about the time interval as measured on the plane. So that's going to be a proper time. So we can use our proper time formula. And we know v and we know delta t. We figured that out in the first two parts of the problem. So we can calculate delta tau. But v is so small here that we're going to need to use the binomial approximation. And then we'll see that we'll get a nice simple expression for that. All right, so delta tau, using that binomial approximation, so that's the binomial approximation. Remember, a square root is a half power, so a is a half, so that's why there's a half here. Then I'm going to write this out, multiply this out. So 1 times delta t, well, that's just delta t. And then minus a half blah times delta t, well, that's minus a half blah delta t. Next thing I'm going to do is I'm going to move delta t over to the left-hand side. And I'll explain why I'm doing that in a second. So delta tau, I'm going to subtract delta t from both sides. Okay. And then this minus sign here, I don't know, when I did this out before, I decided to get rid of it. So let's multiply through by minus 1. So then this becomes plus, that becomes minus. And then that's a plus 1/2 v squared delta t. So now let's plug in some numbers. All right, a half is a half. V, we decided, is this tiny little number, 6.72 times 10 to the minus 7. That whole thing gets squared, and then I need to multiply by 21,600 seconds. All right, so that's a job for a calculator, but a calculator is going to be able to do this. It's over here. So let me deal with this thing first. 6.72 E7 minus 7 squared divided by 2 times 21,600, and I get that tiny little number. And I guess I could count zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9. My calculator will also go to scientific notation for me. Oh, look, and it actually gave me a little more digits when that happens. So this is about 4.9 times 10 to the minus 9 seconds. And 10 to the minus 9 seconds, that's a nanosecond. So this is about 4.9 nanoseconds. So that's our answer. We worked hard for that. It deserves a blue box. So, all right, but what is this? Well, this is the difference in the clock reading. So this is the reading that the time it takes on Earth. This would be exactly 6 hours. And then on the airplane, the clock reads something slightly different. The difference between those two is just about 4.9 or 5 nanoseconds. Certainly not something you would notice on a flight. But atomic clocks, super accurate clocks, actually are accurate to the nanosecond and can measure these types of differences. So to wrap up, using this, all of this is only possible because of the binomial approximation. This business of splitting this apart and getting delta t over here, you can't do that if you're trying to, if you don't have some way to approximate this square root. If we take this square root and we approximate it into the simpler form, then we can distribute the delta t and do this arithmetic in a simpler way and conclude that the clock on the airplane is going to run about 4.9 nanoseconds slow compared to the clock on the ground.